Yeah, so most of your visual field is not in focus, and that's because most of your retina in this area that kind of encodes the light that it's not right in the center of your vision. Those are mainly composed of rods with just a few cones, and things are quite out of focus. The reason they're out of focus is because if we're looking at something, let's say we're looking at, I don't know, like a pencil or something that you're holding up in front of your face. So here you have a pencil. Now the light that comes off of that pencil has to enter the eye at about this angle. Okay, so it enters through the cornea at about this angle. Now when it goes through the lens, this light refracts, or it changes direction as it goes through that lens. And the shape of the lens is going to cause those pathways of light to converge on a point at the exact same point in time that it hits the back of the eye at the fovea centralis. So the fovea centralis contains a lot of cones that are able to transduce the image of the pencil in detail. Now the rest of the retina up here, that's encoding the light that's not in focus, an image that's not in focus. So you can still kind of see what's going on in your peripheral, but it's not in focus. And to illustrate that, if you were to grab, I don't know, a series of colored markers in your hand, hold it up beside your face, but look at a spot that's behind those markers. It's really hard to understand or to determine the order of the colors of those markers in your hand when you're not directly looking at them. And that's because they're simply out of focus. All right, so that's the fovea centralis. One more thing that I wanted to mention here is that the way that these rods and cones are able to encode light, we'll use rods as an example here. They basically are able to encode light because when light encounters these cells, these rod cells back here, it causes a special protein called rhodopsin to change shape, all right? And it basically causes it to break apart, change form and break apart. And when light causes that protein to break apart, that's what kickstarts a series of chemical, or a series of steps that allows an action potential to ultimately be triggered in the connecting afferent nerves. These afferent nerves send that action potential towards the brain through the optic nerve. First goes through the thalamus, and then it goes to the primary visual cortex of the cerebral cortex, and that's basically how we're able to see. One thing that's important, that's actually kind of crazy, is that in complete, I'll make a little chart here, in complete darkness, the rods, they actually are depolarized. So in complete darkness, let's say your eyes are closed in a completely dark room, and these rods are not exposed to any light, we'll have ion channels in the cell membrane of these rods that are held open. That causes positive ions like sodium and calcium to come into the rod, and that causes it to depolarize. When that is depolarized, the bipolar neuron right next to that rod, it actually causes it to hyperpolarize. So it causes the charge in this bipolar neuron to get extremely negative, all the way down to like -70 or so. And when that happens, there is no transmission of the signal to the connecting afferent neuron. So we'll say afferent neuron, we'll say no action potential. However, in the light, what happens is that when light hits these rods, it causes rhodopsin, which is the protein contained in these rods, to change shape, right? That triggers a series of events that closes those cell membranes, or the ion channels in the cell membrane. When they close, positive ions can't come in anymore. If positive ions can't come in, the charge inside that rod is going to get more negative, which is called hyperpolarized. When they become hyperpolarized, that actually causes these bipolar neurons. It prevents them from hyperpolarizing like they did before in darkness. So when these guys become hyperpolarized, they actually allow these bipolar neurons to go back down to their normal depolarization. So they depolarize. When they depolarize, that releases neurotransmitters on the afferent neuron, and those afferent neurons will fire. So they fire an action potential. So the take-home message there is that in the lightness, and when the rods are exposed to light, causes the rods to hyperpolarize, which causes the bipolar neurons to just simply depolarize, which then causes them to communicate with the afferent neuron, telling them to fire. However, when it's dark, the rods are depolarized. When they depolarize, it causes the bipolar neurons to hyperpolarize, which does not transmit a signal to the afferent neuron.